Hello everyone. In this lesson, we will continue to study the frequency domain analysis module of continuous system. In the previous section, we have discussed the decomposition of orthogonal function signal. We can decompose the signal into a complete set of orthogonal functions to discuss the intrinsic properties of signal. In this lecture, we will study the Fourier series expansion of periodic signals and the concept of periodic signal spectrum. The main contents include, first, Fourier series in the form of trigonometric functions. Second, Fourier series in the form of exponential function. Third, the relationship between two Fourier series and their spectrum. And finally, the summary. We can know from the theory of complex variable function when the periodic signal ft meets the Dirichlet condition. It can be expanded into the equation 1, which expresses Fourier series in the form of trigonometric functions. Here, the period is t, the fundamental frequency is omega. Then, the formula 1 is called the triangular Fourier series. Coefficient a0, an, and bn are expressed by formula 2, 3, and 4, respectively, where a0 is the DC component, an is the amplitude of the cosine component, bn is the amplitude of the sine component. You should know that impulse sequence does not meet the Dirichlet condition, so when we carry out the Fourier series expansion of periodic functions of the impulse sequence, we should use a special method. We can also expand periodic function into other forms of Fourier series, such as cosine form, as shown in Formula 5, or sine form, as shown in Formula 6. In Formula 5, periodic signal can be decomposed into linear combination of DC, fundamental wave, and harmonics. Here, the relationship curve between an and omega is called amplitude spectrum. The relationship between phi n and omega is called the phase spectrum. Then, we can draw their spectrum. An is an even function of n omega. Phi n is an odd function of n omega. Obviously, the frequency spectrum of the periodic signal is discrete or harmonic, convergent, and unique. Let's take a look at Formula 7 and 8. Function t can be expanded into a Fourier series in the form of exponential function. Formula 8 is the corresponding coefficient fn omega. When the Fourier series is expanded in the form of exponential function, it is a complex number. Sometimes it can be expressed by fn. Obviously, Formula 7 and 8 are a transformation pair. Formula 7 shows that the periodic signal can be decomposed into linear combination of exponential signal e to the power of jn omega t in the interval from negative infinity to positive infinity. If we know coefficient fn omega, then signal ft is uniquely determined. Since the periodic signal can be expanded into trigonometric form and can also be expanded into exponential form, then what is the relationship between them? Formula 9 is the expression of fn omega. Formula 10 is the expression of f minus n omega. According to Euler formula, fn omega is equal to 1 over 2 times an minus jbm. F minus n omega is equal to 1 over 2 times an plus jbm. So between the two coefficients, they have a relationship of linear combination. Fn omega and F minus n omega are complex numbers, so it can also be expressed by formula 11. Here, the absolute value Fn omega is its amplitude, phi n is its phase. From formula 12, we can find amplitude frequency characteristic, the absolute value of Fn omega. The exponential coefficient is equal to 1 over 2 triangular coefficient. The phase frequency characteristic phi n is described by formula 13. Obviously, an is an even function of omega. Bn is an odd function of omega. The amplitude frequency characteristic is an even function of omega. The phase frequency characteristic is an odd function of omega. Let's look at an example of the spectrum. The picture above is the amplitude frequency characteristic. The picture below is the phase frequency characteristic. Obviously, both amplitude frequency characteristic and phase frequency characteristic are all discrete spectra. Here is a specific case. We know Ft is equal to 1 plus sine omega 1t plus 2 cosine omega 1t plus cosine 2 omega 1t plus pi over 4. Ft is composed of 4 items, where 1 is dc, omega 1t is its fundamental component, and 2 omega 1t is its second harmonic. Let's draw its amplitude spectrum and phase spectrum. First, in order to draw their spectra in trigonometric form, we first convert Ft to cosine form. We can get formula 14. Combine 1 and cosine 2 omega 1t plus pi over 4 to get the middle item. Cosine 2 omega 1t plus pi over 4 is still retained in formula 14. Then we can get the coefficients of their spectra in trigonometric form. A0, A1, A2, phi 0, phi 1, phi 2. In this way, you can get a spectrum in the form of a trigonometric function. The left is its amplitude frequency characteristic. The right is its phase frequency characteristic. Let's turn Ft into an exponential form. According to Euler's formula, we turn the sine and the cosine function respectively into the form of exponential functions. Therefore, we can get the formula 15. The coefficients of Fourier series in exponential form are f0, f omega 1, f minus omega 1, f2 omega 1, and f minus 2 omega 1. According to the coefficients, you can get the spectrum in exponential form. The top left is the amplitude frequency characteristics. The top right is the phase frequency characteristic. Let's compare the spectra in the form of trigonometric function. We can find that the spectrum in exponential form is bilateral. The spectral lines appear on both sides of the vertical axis, while the spectrum in trigonometric form is unilateral. The spectral lines only appear at 0 and at its right. Observe these two figures. We can see the height of exponential spectral line is 1 over 2 times that of its spectrum in trigonometric form. To sum up, the content of Fourier series expansion of the periodic signal are as follows. First, the periodic signal can be expanded into two forms of Fourier series. The first one, Fourier series in trigonometric form. It is characterized by a unilateral spectrum. The second one, Fourier series in exponential form. A spectrum is a bilateral spectrum. The relationship between the two spectra is shown in Formula 18. The phase spectrum is an odd function. The amplitude spectrum in exponential form is an even function. In addition, you should notice that the frequency spectrum of a periodic signal has three corresponding properties. First, convergence. That is to say, when n tends to infinity, its spectral coefficient is close to zero. Second, frequency spectrum of the periodic signal is harmonic or discrete. Its frequency only appears at n omega. Third, uniqueness. That is to say, the frequency spectrum of Ft is unique. Here, you should note, when periodic impulse function sequence does not meet the Dirichlet condition, we should use other methods to do Fourier series decomposition. We will discuss this point in following course. Finally, when discussing the frequency spectrum of a periodic signal, we introduce negative frequency. For bilateral spectrum, the negative frequency minus n omega is meaningful only in mathematics and meaningless in physics. The appearance of negative frequency is entirely the result of mathematical operations. Only by combining the negative frequency term and the corresponding positive frequency term, we can get the extra spectrum function. The concept of periodic signal spectrum is very important for us to understand the characteristics of frequency domain of periodic signal and to review its physical nature and its application in engineering. I hope you can review the knowledge you learned today seriously and master it. This class is over. Thanks for your attention. Goodbye.